Okay, welcome everyone to this session of the seminar on PDEs and applied mathematics that we have been celebrating since 2020. Today we have the honor and pleasure to have with us Professor Monica Musso, a magnificent mathematician from the United Kingdom. She obtained her PhD in 1997 from the University di Pisa in Italy, and after that she was a postdoctoral researcher in the International School for Advanced Studies in Trieste. Then she worked at the Politecnico di Torino in a permanent position, and since 2004 at the Department of Mathematics in the Universidad Católica de Chile, becoming professor in 2012. Nowadays, she works as a professor in the Department of Mathematical Sciences of the University of Bath, UK. And we can also mention that she has obtained different research grants, she's part of several journals' editorial boards, mentored various PhD students, and organized and participated in a large amount of conferences. She is also a member of the Chilean Academy of Science. She works in the area of nonlinear analysis and partial differential equations, and some of the topics she is interested in are singularity formation in elliptic and parabolic equations, concentration phenomena in critical problems, and fractional Yamabe problem. So thank you very much, Monica, for having accepted our invitation to give this talk and sharing your knowledge with us. All yours, Monica.
Thank you very much. Well, first of all, I would like to thank the organizer, Professor Juan Limaco, for the invitation. It's an honor for me to be here. And many thanks, John, for the introduction, very generous introduction. Thank you. In this talk, I would like to present a result on what is called the liquid drop model, and a recent construction that we did together in collaboration. I will mention them later, with Manuel Del Pino from Bath and Andrés Zúñiga from Chile. So this model, the liquid drop model, was introduced by Gamow in 1928. What he did, he introduced an energy. This energy is a functional that is defined on region omega of R3. These regions are open set and bounded. And to any of these regions, this energy associate the perimeter of omega. And here we will talk always about smooth region. So you can think of the perimeter as the area of the boundary of the three-dimensional set omega. So this is the perimeter, the first term of the energy. And the second term of the energy is a double integral over omega of this interacting term, 1 over x minus y modulus. So why Gamow introduced this energy? This represents the energy of a nucleus. So the nucleus is made by protons and neutrons. They are called nucleons. And the assumption is that these elements here, protons and neutrons, are uniformly distributed in this region omega. So that when we talk about the volume of this region, this is equivalent, or it's proportional to talk to the total number of nucleons or the mass of the atoms of the nucleus. Okay, so what are the meaning of these two terms in the energy introduced by Gamow? So the first term wants to represent the surface tension that keeps all the protons and neutrons together. So the perimeter is what maintain this object together, these particles together. On the other hand, if you have protons and they interact with each other and they repel each other, and this is the meaning of the second term of the energy. So this is the column repulsion between these nucleons. So this is the meaning of the two terms of the energy. And what you define is the ground state of a nucleus is given by when you can minimize this energy among a domain with a given mass. So you are given a mass or a volume, a number m, and you try to minimize this energy among all domains with that given mass. All right, what we will see is that ground states, these minimizers, exist at least when the mass m is small, while they do not exist when the mass m is large. But let me just mention something else, which is a very nice paper by these two physicists, Bohr and Wheeler, in 1939, because they were interested in nuclear fission, and in particular, the question was, what is the minimal energy at which you get nuclear fission? So this obviously doesn't occur at a minimizer, so you look for other type of critical point of this energy, not necessarily minimizer. So what does it mean to look for critical point of this energy? Well, what we mean is the following. We want to have a critical point, so the first variation of something has to vanish, but it is the first variation with respect to normal perturbation of the boundary of this domain omega that have the property that preserve the volume. And in fact, and this is something that I would like to explain a little bit, when you look for critical point of the energy, basically what you are looking for are region omega of a given volume m, so that if you compute the h, so this h here is the mean curvature of the surface. So you have the boundary of omega, it's a surface. You take a point x on the boundary of omega, and you compute the mean curvature of the surface. So this is a function of x plus this integral here equal to lambda. Lambda is a constant, is the Lagrange multiplier. So a critical point of the energy E is a domain omega with the property that if you compute the mean curvature of the boundary plus this integral at any point x on the boundary, this gives you a constant. Let me try to do a very little computation to convince you that in reality, yes, when we look for critical points of E, we are solving this equation here, this problem here, P. The reason is simple. So we look for a normal perturbation of the domain omega. If I call sigma the boundary of omega and nu the unit normal to sigma, and I defined a function little h on sigma, I consider the surface sigma h, which is basically, it is sigma, it is given by points in sigma y plus a perturbation h in the normal direction. So this is a perturbed surface, and the volume enclosed by sigma h is omega h. So what we want is, we want to compute the energy in omega h and compute the first variation equals, remember that we want to have a given mass, a given volume, so equals to lambda, a Lagrange multiplier, times the first variation of the volume with respect to this normal perturbation. And this is a very simple computation. If for the energy I consider the Coulomb interaction, now computed in omega h times omega h, minus the Coulomb interaction on omega and omega, this is just, so when you integrate on omega h, you write omega h as omega union omega h minus omega, and this is the computation that you get. And so this difference here is like the integral over the boundary sigma of omega of h times this integral here. It's even simpler when you want to differentiate the mass. The mass on omega h is the integral over omega h that you split in this way, and so you get this. With the perimeter is slightly more complicated, but there is a very simple formula that you can use. It is convenient for the perimeter to recall that you are computing the area of the boundary. So if you parameterize the surface sigma, so this is a parameterization of sigma. Sigma is a surface, a two-dimensional object, so this omega is omega 1, omega 2. You can parameterize in this way the perturbed sigma h. And then the area is just the integral over the space of parameters, omega, of the square root of the determinant of the metric induced on the surface. And you can compute easily the metric. It's this matrix is a 2 by 2 matrix, and where YH is just the derivative in the parameter of this function here. And the nice thing is that since we are in 2 dimension, we have a lot of computation that can be done in a very explicit way. So this matrix here is equal to the matrix corresponding to H equal to 0 times the identity matrix plus H times capital A square, where capital A square is basically the second fundamental form. Here B is the matrix, the derivative of the normal. And when you do the determinant of H and you take the square root, it's really an explicit computation, and you get, remember, we want to differentiate, so in H, we are interested in the linear terms in H. So what you get here is the trace of A. So when you put this computation in the formula, you get that the derivative in the direction H of the area is equal to an integral over sigma of the trace of A, which is nothing but the mean curvature of the surface. So if you put everything together, you see that a constrained critical point of the energy with respect to normal perturbation satisfies this equation for any H defined on sigma, and H appears here, here, and here. And what you boil down is to find domain omega, so that if you compute on the boundary of this domain the mean curvature plus this, you get a constant. So this is problem P that we want to address. All right, let me just compare briefly the computation we just saw with another computation that involves only the perimeter. So when you look for a critical point of the perimeter subject to volume constraint, so you drop the Coulomb interaction, this corresponds, then you don't have the integral of 1 over x on the boundary, and this corresponds to finding surfaces sigma whose mean curvature is constant. And we know that from Alexandrov that surface sigma that are bounded and embedded have constant, if they have constant mean curvature, then they are the boundary of a ball. So ball, if we remove the perimeter, in the set of bounded and embedded solution, balls are the only solution. All right, but let's go back to our problem where we do have the Coulomb interaction. The first observation is that also for our problem, balls are solutions. And balls of any volume are solution because both these terms are constant if computed on balls. Let me be more precise. We know from the classical isoperimetric inequality that balls of volume M are minimizer of the perimeter. So in particular, the mean curvature of a ball is a constant. But also from Reed's 1930, balls of volume M, they maximize the Coulomb interaction. So in particular, this term here is also constant. So for two different reasons, balls, they do minimize the perimeter and they do maximize the Coulomb interaction, but they are always solution for any value of the mass M. All right, but even in the case of balls, we see that balls minimize the perimeter and maximize the other part of the energy. So there are here two different effects of one of the two terms of the energy. And to see this, we can perform a very simple scaling. So our domain omega has mass m, so it can be written in this way, m to 1/3 times E, whose volume is 1. And if you replace into the energy, you get this expression. So apart from this factor here, m to 2/3, you see that this energy is the perimeter of E plus m times the Coulomb interaction of E. So we can think that for small mass, when this m is small, what we see is the perimeter. And since balls minimize the perimeter, we can think that for small m, what matters is the perimeter, and so we have minimizers. But for large m, what matters is the Coulomb interaction. So we can think that for large m, we do not have global minimizers. And in fact, this is more or less true. There is a very special number here. It's called m star. It's a very explicit number. It's this ugly number here. It's 3.51. And it is the number such that if you compute the energy of a ball of mass m star, and you compare it with the 2 times the energy of the balls of mass m star over 2, these two energies are the same. Okay. There is a unique m star that does this. So the energy of the ball of mass m equals 2 times the energy of the ball of volume mass m over 2. And in fact, you can prove that if your mass is bigger than this very weird number, m star, then the energy of the ball of mass m is bigger than 2 times the energy of 2 balls of volume m over 2. So you can think that if you take these 2 balls of volume m over 2 and you put them very far away from each other so that the Coulomb interaction is negligible, and you glue them with a tiny tunnel, the energy will be lower than the energy of the big ball. So in particular, for m bigger than m star, balls are not a global minimizer anymore. There is a better minimizer, two smaller balls far away from each other. Now, there is a conjecture that is still open, and it says that if the mass is less than m star, then the infimum is achieved, and precisely when omega is a ball. But for m greater than m star, the infimum is not achieved. There are some partial results in this direction. A series of papers in the same year, in 2014, proved that there exists an M1, but they don't quantify what is M1, less than M star, for which if you are in between, for mass less than this M1, balls are minimizer. So for small mass, balls are minimizer. Recently, after 10 years, Chodosh and Rao Niemi, they could quantify this M1. So they proved that for any mass between 0 and 1, balls are minimizer, but 1 is still strictly less than M star. So in the region between 1 and M star, it is still not known whether balls are minimizer. It is known that in this range, there exists a minimizer. It is known that for large mass, there are no minimizer. And it is known that for mass bigger than 8, minimizer do not exist. So let me, this is, so there are several masses here. So small mass balls are minimizer. Up to M star, there exists a minimizer, but in this range here, it's not clear whether balls are the minimizers. After this M star, balls no longer are minimizer. From 8 on, we know that there are no minimizer. And yet there is another number, this number 10, because balls are always solution for any value of m. Here they are minimizers, and they are local minimizer up to 10. Here they are global minimizer. But up to 10, they are local minimizer. At 10, crossing this value, they gain one Morse index, and they become mountain passes, not anymore minimizer. They are still critical point, but not anymore local minimizers. So this number 10 is weird, but it's important. So what happens at the value 10? So this is a picture that I took from this paper of Xu and Du in 2023. And this chi-star here, sorry, is they use other constant in front of the perimeter and in front of the Coulomb interaction. So in their paper, they have different constants, but this chi-star correspond to our 10. So at mass 10, balls, they are not anymore local minimizer, and they gain one Morse index. So there is a possible bifurcation point. And in fact, Frank in 2019 proved that there is such a bifurcation. So, and in fact, the ball which correspond to this line here, exactly around the mass 10, it bifurcates to the left in a solution that is has this shape. It's a prolate, and on the right it's oblate. So for large mass, say 10, there are other solutions other than the ball, and Frank proved the existence of this solution via bifurcation. Now you may ask whether for higher values of M you get further bifurcation, because balls are always solution, but they gain Morse index when mass increases. And in fact, there are other higher values of M where you can see bifurcation, and this is an ongoing paper or result in collaboration with De Regibus and Grossi. But let me go back to the famous Bohr-Wheeler paper. These people are physicists, but they know experiments, they know physics, they know how things work. And this picture is taken again from this numerical paper of Xu and Du in 2023, where basically this picture is telling us the following. At mass more or less 10, we have the ball, and then this picture follows this bifurcation branch, which is called the Bohr-Wheeler bifurcation branch, that Frank described more or less close, in a region close to mass equal to 10. In fact, Frank proved that if you go to the left, smaller mass, you get a prolate. But then numerically, you can see that if you decrease the mass, this domain starts to lose convexity. And for smaller masses, you get a solution of this form along the Bohr-Wheeler bifurcation branch. So that they seem to be two balls linked by a very tiny neck. On the other side, for mass bigger than 10, then you see the oblate of Frank, and then numerically, this has not been proven analytically, you see a sort of donuts coming out. Okay. A result in 2011 by Ren and Wei is probably one of the first results of existence of solution, not necessarily minimizers, for very large mass. What they prove is that for very large mass, a tori of this form with a bigger radius, very large, of the order m times log m to 2/3, and it's a very thin tori, so there is a smaller radius here of this with these asymptotics, is a solution of the problem. So this was constructed by Ren and Wei. These solutions are axisymmetric, so in reality they use the natural axisymmetric symmetry to reduce this three-dimensional problem to a two-dimensional problem. Let me mention here that there is a very nice paper in the notices of the AMS in 2017 that describes this problem by Chosky, Muratov, and Topologlu. All right. So this is the result that I would like to present. And to present this result, let me recall one important family of constant mean curvature surfaces, we already mentioned that the problem of constant mean curvature surfaces is very much related to this problem. And there are a family of non-compact CMC surfaces. These are called the Delaunay surfaces, so they are not bounded. They come in a family. There is a parameter here. For any A, you get in a certain range, you have a Delaunay surface. These are a surface of revolution, and they are periodic, and they have constant mean curvature. Let me say that the constant mean curvature is 2. Part of this family is the cylinder, but there are these kind of onduloid, and that you can see here, the form. And for parameter A equal to 1/2, you have the cylinder. For parameter A equal to 0, you have this picture here that are balls touching tangentially one with the other. And then you also have not embedded surfaces that we are not interested in. So what we want to do is to use these Delaunay surfaces as a building block to construct a new solution to the liquid drop model. So this is one of the pieces of the Delaunay surface. Since it's a surface of revolution, you can describe this surface as so you write your point x in R3 as x bar in R2 and x3, and then the radius, so the modulus of x bar is a certain function f of x3. So here x3 is the horizontal axis. And this function here, f, is periodic. The period depends on A, but we can assume that it's a given function, it's well known, and you can assume that it is even in the x3 variable. So a whole Delaunay is just a union of these necks. Now take just n of these parts. Just cut your Delaunay, just n of those. This is what we call sigma n. And then consider the perturbation in the normal direction of sigma n and call it sigma n h. So you take a part of this Delaunay, sigma n, and then you perturb normally with h. Now, if you introduce a number capital R that is related to the n parts that you take and the period t by this relation, you can take this part of the Delaunay, you can rotate it in the plane, say x2, x3, and this rotation is glue this surface well in a sort of new surface which has this shape, the shape of a collar. Okay, provided you choose the r, which is the distance of from the center to the surface in this way. So you get this surface. Imagine if this is a Delaunay simply rotated. And since you have this smart choice of R, it closes well. And you get this color. And here, these are just formula. let me just mention the following. You can describe precisely what this rotation is this map X. So whenever you see a tilde, it means that it is rotated. If you don't see a tilde, it is straight. And so sigma NH is the straight Delaunay and contains a three-dimensional region, and sigma tilde NH is the perturbed Delaunay but curved, rotated, and it contains a domain that we call omega tilde NH. Okay, it is more clear the picture than all these formulas. All right, so the result that we have is that indeed, and this is a result in collaboration with Manuel Del Pino from the University of Bath here, and Andrés Zúñiga from Chile, is that for very large mass, you can find a solution to the liquid drop model in the form of this collar. So in other words, you can, for any m large, you can find a domain omega of mass m. This domain omega has a certain form, is a certain multiple of the collar. This number gamma is related to the number of necks that has this collar. So this number gamma is C divided by log n. The mass is related to the number of necks, of course, is of the order n divided by log n. And the perturbation, h, is of order 1 over log n. And you can find this collar, this big collar with n necks, in such a way that you get a solution to the problem. So if you compute the mean curvature on the boundary of this region plus the Colombian interaction, you get a constant. I would like to take 2 or 3 minutes to present the proof of this theorem. And I have 2 or 3 minutes left. Basically, there is a first step that by scaling, you can the problem that you solve is equivalent to solving a new problem with a gamma here. So we want to find a twisted Delaunay solution to this P star problem. There is an integer, there is a number I sub a, that is this integral here. F is the function that defines your Delaunay. That is important. We need that this number is positive, but it can be proved for certain range of a that this is positive. And the main proposition is as follows, that for any sufficiently large integer n, we can construct a solution to the problem for that looks like this rotated Delaunay. So for any large n, we can find a solution with mass proportional to n divided by log n, a solution of the problem. And the proof is based on a Lyapunov-Schmidt type of argument. But here we construct for any large n a domain of volume, say, n divided by log n. but we are not sure that this construction covers all possible large masses. Maybe we just cover masses of the form n divided by log n, but we want to cover all possible masses. And this can be done by a continuation argument and a uniform control on the estimate in the previous part of the proof. Let me mention one last thing. In the Bohr-Wheeler bifurcation branch, we saw that for small masses, there are solutions that looks like two spheres linked together by a small neck. And using a different kind of proof, we can prove it. And this is in collaboration with Manuel Del Pino and Rupert Frank. For each small mass, we can find a solution to the liquid drop model with this shape. It's the union of two balls. Each ball has a volume m/2, and the neck is a catenoid. The size of the neck of this catenoid is of order epsilon, which is proportional to m. So we could describe this first part of the Bohr-Wheeler bifurcation diagram in this late result. Okay, I think I can stop here. Thank you very much for your attention.
Thank you, Monica, for your great presentation. I think that I don't know if someone in the audience wants to ask something or do some comments. Juan usually opens the micro to give the possibility to the people to ask something. Yes, meanwhile, I would like to say that I have enjoyed because you have presented these kind of problems that have been studied since a long time ago, no? And how the size of the or the value of the M, the mass, no, was a problem when you were having a large a size of the volume, no?
That's right. That's
Yeah,
right.
and at the end, it seems that after some years, people started to study more what happens for large masses, no? And then,
Yes,
yeah.
yes. There are very few results for large masses. So until recently, sorry, I wanted to look for this. So until recently, the only thing that it was known was that balls are solution for all value of the mass. But construction of solution for large mass, well, there is this construction of Ren and Wei for very large mass. There is this bifurcation result around the mass equal to 10 by Frank, and there is our results that is for large mass and under no symmetry assumption. But yes, why? Because, well, the point was to establish that for large mass, there was no minimizer. So this solution with large mass can't be obtained as a minimizer of the energy. They arise in a different way. They are different kind of critical point of the energy.
And one of the reasons why you can control or try to minimize this problem could be the Coulomb interaction inside, no? Because you said that that term is doing you that you can many if the mass is very big, no?
Oh yes, the Coulomb interaction. If there was no Coulomb interaction, we would be fine.
Yes.
But the Coulomb interaction is, for large mass, is what seems to be important. And for instance, for balls, the Coulomb interaction is maximized. So you don't expect, in fact, it is known that it is not, you don't have minimizer for large masses. But let me mention, it is believed that for any mass bigger than this m star, there is no minimizer, but it is not known. It is known for masses bigger than 8, but in between m star and 8, people believe that there are no minimizers, but it's an open problem. And the same open problem is here, because people believe that between 0 and m star, balls are the minimizers. It is known only between 0 and 1. But between 1 and m star, we know that there exists a minimizer, and people believe that that minimizer is a ball, but it's not known.
Yes, it's very curious.
It's very nice. It's very nice indeed.
Yes,
Yeah.
how you
Yeah.
have presented all the history of the problem. I have one more question, but I will give the possibility to the audience if there is someone that wants to ask something here. No, anyone? If not, I was very curious because I was surprised why or in which moment you have realized that the Delaunay-like surface could be appropriate to obtain a result, no, for this complicated problem. So why that specific surface? No?
Absolutely. It is a constant mean curvature.
Ah.
And there is this link between this problem and the constant mean curvature problem. So if you don't consider the bad guy, the Coulomb interaction, the solution are surface with constant mean curvature. So the Delaunay is one of them, but it is unbounded.
Yes,
So this can't be used.
in order to bound it.
To bound it, we close it.
Yes.
And since it is, if you take a very long Delaunay and with n blocks and n is large, you need a very long radius to close it.
Yes.
So since it is a very long radius, locally you see that the Delaunay is almost straight,
Yes.
because the radius is very large. And then we tried, and then it happens to
It's very ingenious. Yes.
yeah, it was nice. It was interesting. Yes.
Yes. So if there is no more questions, thank you, Monica. It was really nice to listen to your talk and hope to see you again here.
Thank you very much. Hope to see you too soon.
Yeah.
Thank you.
Thank you, Professor Monica, for your
So
excellent talk.
I